Hi, good day, and thank you for taking the time to view our web demonstration today. My name is Marcus, and I'll be your application specialist, taking you through today's web demonstration on the Faro Edge ScanArm. We will be taking measurements on this part, which I have placed on my table, and during the demonstration, I will change to an overhead view so that you will get a better idea of how the measurements are made. Before we proceed with today's demonstration, I just have a quick PowerPoint presentation to share with you. So we will be doing the Faro Edge ScanArm web demonstration today, and our agenda for today would include firstly a Faro company overview, followed by a system review of the Faro Edge ScanArm, where I'll share with you some of the hardware specs of the Edge ScanArm. And then following this presentation, we will move on into a hands-on inspection, which is the meat of today's demo. And we'll be doing firstly some basic measurements and inspection on this black demo plate without the presence of a CAD drawing. And later on, we will introduce a CAD drawing, and you will be able to see once you introduce the CAD drawing how more measurements and comparisons can be made. And finally, when you are done with the uh, measurements, you'll be able to generate a report from the software as well. So we expect the duration of today's demonstration to last about 30 minutes, and we hope to discover applications for this technology within your company's needs. Faro began in 1981 in the medical 3D component industry with the articulating arm technology, and the Edge scan arm which you see on the table today is the latest iteration of this articulating arm technology. We transitioned from the medical industry to the industrial manufacturing markets in 1994, and over the years we have come up with different kinds of equipment which we will share in a later PowerPoint slide with you. Our global footprint consists of our global HQ in the US in Lake Mary, Florida. The European headquarters is located in Germany, and the Asia Pacific headquarters is located in Singapore. For today, we will be going over the Edge scan arm, so I will share details about it in my later slides. But for now, I will just go quickly over the other equipment that we have in our product family. So beginning with the Laser Tracker Vantage S, this is a coordinate measurement machine. And how it works is that it fires out a laser to be captured and reflected by an SMR, which contains 3 mirrors. And with this reflected laser beam, you'll be able to measure distances and different types of dimensions on your part up to 80 meters away. We also have the Cobalt Array 3D Imager. A single unit will be able to scan a part and generate a point cloud from that. And you can actually do a alignment with a CAD drawing in order to have a deviation comparison. If, for example, the part that you intend to scan exceeds the field of view of a single unit, you can combine them in an array in order to cover the entire surface area of the part you are scanning. For the laser projector Tracer M, it is a laser projector which is able to project a green laser line in the shape of various features on your part. So what it does is that it replaces the need for physical templates. So you can use the laser lines to guide you for processes such as ply layup, or you can also use it to determine drilling points or welding points or placement points for parts for assembly. For the Focus 3DX series, it is a portable laser scanner used mainly for building information modeling or civil information modeling, where it can scan building facades or rooms, or it can be used for crime scene or accident scene scanning and analysis. And the Freestyle 3D scanner is a handheld scanner that is more suitable for product design or reverse engineering purposes. So we offer a suite of software to work with our hardware, and we also offer support for third-party software such as GeoMagick and Polyworks with our hardware. For now, I will share with you some of the hardware specs of the Faro Edge ScanArm. So as you can see from my slide, the first point mentions that this is a contact and non-contact measurement system. So if we look at the camera, you'll be able to see that we have a 6mm ball probe installed, and this ball probe is used for contact measurements, which I'll show you during the demonstration. You can also change the ball probe from the 6mm to a 3mm option for smaller features, and you can also change it to a soft probe to measure soft surfaces such as car seats. And for the non-contact measurement system over here, along the bottom, we have the laser line probe here installed. And this will be able to project a blue laser, which will be able to capture point cloud scans of your parts. So I'll show you this during the demonstration as well. The construction of this arm is carbon fiber. So as you can see, it's very lightweight. It's 10.9 kilograms. And with the presence of this internal counterbalance, we are able to easily maneuver to your part for measurements. There's also 7 axes of movement. As you can see from my PowerPoint slide, the various circles depict the axis of movements. And this arm is available in 6, 9, as well as 12-foot configurations. And what this refers to is actually the diameter with the arm positioned in the center. So respectively, you will get 3, 4.5, and 6-foot radius from the center for measurement. Moving on to the front panel over here, if I pull it down, you'll be able to see that there's also a rechargeable battery, which will provide you with 4 hours of operational time with one full charge. And there are various connectivity options provided as well, so you can connect the arm to your computer via USB, via Wi-Fi, or via Bluetooth. The accuracy for this arm, so for a single point accuracy, we have 29 microns, and for a volumetric accuracy, we have approximately 60 microns. So, looking at the applications of the ScanArm, you can see that it's very suitable for non-contact inspection with the laser line probe. You can use it for first article inspection to easily measure and compare your prototype parts to the nominal data. Again, this can be done with both the contact probe and the non-contact laser line probe. You can perform CAD-based inspections by importing your CAD drawings into the software for comparison with your live physical measurements. And you can use the arm for reverse engineering as well from the point clouds that you scan. And just to give you a quick overview of the relevant industries which the ScanArm can be found in, it's very suitable for automotive and aerospace, defense, education, in foundry industries, in the heavy machinery industry, in the medical industry, as well as in the oil and gas industry. So this brings me to the end of the PowerPoint presentation, and I'm ready to begin the web demonstration for the Edge ScanArm. So I will firstly change my camera view to the overhead camera view. And as you can see, I have clamped the black demo plate onto the granite table over here, and we are ready to perform some measurements. My arm has been connected to the software already. And as you can see, for the Cam2 Measure 10 software that we are using right now, it is a familiar Windows-based layout with all the main tabs along the top. And to begin your measurements, all you have to do is move into the Measure tab. And as we are going to be measuring features on the top plane of my part, I will firstly measure a reference top plane where the features are located. And I'm using the contact measurement right now. So as you can see, I'm touching the ball probe onto a point on the part, on the plane. And then I just press the green trigger button over here to take a point measurement. And if you look along the bottom left corner of my software screen, you'll be able to see a real-time feedback on the coordinates taken and the flatness of the plane measured. So next, I'll be measuring a line. And I'm going to be measuring a few circles on my part. So I'll be measuring the center circle firstly, followed by all these little circles, and I'll show you how you can also construct pitch circle diameters from other circles or these small circles which we've measured. So we're going to begin with the contact measurement of the circle. Again, we touch the probe to the inner circumference of the circle that you are measuring, and you take a point measurement, and we move along the inner circumference and take additional points. And again, as you can see in the bottom left corner, you'll be able to get a real-time feedback on both the diameter Okay, let me begin that again. So we'll be taking measurements on the inner circumference of this main center circle firstly. And one of the first things you will notice is that you get a real-time feedback on the diameter of this circle that we're measuring, as well as the circularity. And then I'll be taking all the smaller circles as well. So let's review the measurements that we've taken. If you look in the software screen, as you can see, I have not introduced any CAD drawing at this point. So what we have are the 3D representations of the physical measurements which we've taken. And you can see the plane that I've measured along with the line, along with my center circle and each of the individual smaller circles. If I go into a particular feature and I pull out the feature information, if you look, we have details on the center circle such as the X and Y and Z coordinates, the diameter and the circularity. If you know the nominal data for this circle's diameter, you can key it in. And what you will get is the immediate value of the deviation between the actual and nominal data, as well as whether or not it passes your out of tolerance test. And for the tolerance, you can also determine the upper and lower tolerance values for this feature on this part. So the same goes for each of the other features which we've measured. So we get again the XYZ coordinates and the diameter and the circularity of each subsequent feature which we've measured. So I mentioned that you can also construct something like a pitch circle diameter. So from the smaller circles which we've measured, I can construct a pitch circle diameter from them. So this is circle 10 which has been just created, and I can rename it. And again, if we look at the pitch circle diameter, once you construct it, we get the same XYZ coordinates and the diameter and the circularity. And again, if you know the nominal information, you can key it in. You get again the out of tolerance pass or fail, and you can also change the tolerance requirements for this feature. You can also do something like measure the length between two features which you've measured. So I can measure between circle 1, 2, 3, 4, 5 and 5. So we have the radius over here between circle 1, the center circle, and circle 5. A label appears for each of the features and analysis that you do, and you can choose to have a detailed label for them as well. So if I choose to have a detailed label for the length, it will show up as such. I can choose to have detailed labels for certain features as well. Or if we change it to a simple label, it will just appear as circle 2. We can also do a angle analysis. So if I choose 3 points, then I'll choose 2, 4. So here we know that this angle between circle 2 and 4 is 90 degrees. So this is indicated as 89.985 degrees on my measurement. And you can also choose to have, again, a detailed label for this angle that you measured. So with these basic measurements that you've taken and basic analysis such as angle and length, you can also generate a report already from these measurements. So if I click on the report tab, I can include all the features which I've measured in my report, and we get to see a real-time view of what the report will look like before we export it. So you can change the company name, logo, as well as the address and contact information. Under the session information, you'll be able to update the operator name, company name, things like that. The view over here for your report will come from the last seen view in your software screen. If I scroll further down again, we get the angle that we measured, the plane that we measured, the line, and each of the circles that we've measured, we get the actual values measured. For the pitch circle diameter that we created, we also have the actual measurements. And for the length, again, we have the length as well as the XYZ coordinates. The next thing I want to show you is some basic GD&T. So if we would like to, for example, compare the flatness of the top plane of my part with the table, we can do so. So I've measured the top plane of my part. I'll just call it plate top. I can measure the table as another plane. I can call the new plane that I've measured, I'll just name it as table. And if I go into the GD&T mode, I can assign datums to these two planes. So I can assign this as datum A, the plate as datum B, and I can then check the parallelism between A and B. So here we have the parallelism between A and B. If I close it and I indicate a detailed label for plane, the table, and for our plane, so we get the difference again indicator over here, the parallelism between A and B. You can also check concentricity between two cylinders. So if I measure a third plane for this inner cylinder over here, and then I measure two cylinders, one being the same circle as my center circle, and the other one being the inner cylinder. So you can see that we've measured two cylinders, one larger and one smaller. So if I go into the GD&T, I can again include the two cylinders which I've measured. I can assign them another two datums, in this case C and D. And I can then check, for example, the concentricity between C and D. So again, we get the concentricity of about 300 microns. So if I indicate a detailed label, you'll be able to see the cylindricity of one cylinder and the concentricity between C and D over here. So again, once you're satisfied, you can go into the report and I can include now the additional features which I've measured. And the report will automatically update. And now we see the parallelism between A and B over here indicated. As well as the cylindricity and concentricity for C and D over here, cylinder 1, cylinder 2. And once you are okay with your report and your analysis, you can actually export from this software directly to CSV, PDF, text, or Excel. So this brings us to the end of the first part of our demonstration where we're actually doing all these measurements on the actual part. We get the real-time readings on each of the measurements that we've taken. And all these are so far performed without the presence of a CAD drawing. So what happens if you have the CAD drawing for your part? So if I import my CAD drawing, the first thing you will notice is that my CAD drawing is here in black and it's not aligned with all the measurements which I've just taken. So if I go into alignment, I can create alignment between the measurements which I previously taken and the CAD drawing. So if I create that, you'll be able to see that right now, all my measurements are now aligned with the CAD drawing which I just imported. And the usefulness about this is you'll notice immediately under cylinder 1 that the diameter, the actual data is what we've measured, but the nominal data from the CAD drawing has also been imported, and we get the deviation readout as well. So if I go into the feature information for each of the circles as well, you'll be able to see that the nominal data from the CAD drawing has been imported automatically to compare with my actual measurements. And this is the same for all of the features over here. So other things that you can do as well once you have performed alignment between your CAD drawing and your measurements is you can actually inspect surface points on your part. So for example, you have certain features or areas on your part which you always have to inspect the surface of. You can move the probe directly to that point. The real-time feedback is given in the software screen, so wherever I move my probe, you can take a measurement there. I take a measurement at that point, you can see immediately we get the deviation value at that point. So I can take another point over here, and then again we get the deviation value for that point. And for the center portion, I know that it is off by about 2.3 mm. So if I take a measurement there, measurement here, we see the deviation as 2.3 mm under compared to the actual CAD measurements. So again, if I close this, again you can generate a report based on those inspection surface points which you've done. And if you would like to see more than just single point color deviations, you can actually do a sweep across the entire part. So again, so far we have been using contact measurements, and right now I'm going to show you how the laser line probe can work. So firstly, I'll take a scan and sweep over the top plane of my part, and you'll be able to see a color map across the image on the software screen. So you can see the blue laser line being aligned with the red crosshair in my video feed. So once the red crosshair and the blue laser line are aligned, there's a green LED indication on the arm. If I move away and it's out of focus, the light turns red. So I'll move it to ensure that it's green. And if I sweep across, you'll be able to see the color map instantly being compared to the CAD drawing which I imported. So I'm going to hide this top plane so you'll be able to see a little bit more clearly. So as you can see, we have a color map across my part, and you can see most of the areas are colored in green, which means that it's within tolerance. I told you that the center portion here is under tolerance. So if I change the point distance filter for this point cloud under properties, be able to see that the center area is colored in blue because the whole center portion here is under tolerance. So you get an instant feedback based on the color map of this point cloud which we've measured, and you can compare that with the color scale on the right hand side to determine how much out of tolerance within or within tolerance the part is. And you can also change the tolerance for the point cloud both in the upper and lower tolerance field. So if you make it tighter, you see that the color changes according to the tolerance which you've changed for the part. So again, if we go into the reporting screen and I include the latest features which we've measured, you'll be able to see the surface points which I inspected and a summary of the point cloud which I took. So you can tell at a glance how many of the points of the point cloud are under, within, or out of above tolerance based on the tolerance settings for the point cloud which I changed earlier. So this brings us to the end of the main first part of the demonstration with the edge scan arm. I just have a little bit more to show you, and I'm going to change out to this part which I'm showing in the camera right now. So this is a pretty free-form shaped part, and you can see there are various features on all the planes of the part, and there's a teardrop shaped bulge along the top plane of my part. So this is to show you how the laser line probe is also very suitable for non-contact scanning of very free-form shaped parts. So I'm just going to swap out and very quickly I'm going to take a scan of this part. So I'm going to start a new project. Going to measure, select point cloud, and we can quickly obtain point cloud scans of any part. So I'm gonna stop this, and you can see that we can easily obtain a point cloud scan of your part. We've captured a bit of the table, but that can be easily removed by measuring a clipping plane using the table. So if I go into the point cloud properties, we can measure a clipping plane. And if I hide the plane, you'll be able to see that we just have the point cloud over here. So from this point cloud that we've measured, I talked about reverse engineering purposes. So you can export this point cloud directly to a mesh. And I'll just quickly show you that you can obtain an STL mesh of any point cloud that you scan very easily within this software as well. If you have the CAD drawing for your part, you can import it. Again, they are not currently aligned. So if I perform an alignment, you see that the software automatically tries to align the point cloud on my right with the CAD drawing on the left. And with that alignment, you are able to obtain a color map across your part. You can tell which areas are again above, within, or under the tolerance based on the color scheme and scale on the right hand side. We know that this area is under tolerance, so we can create some further analysis at this area using deviation markers. So if I zoom in, you can see that it's created a grid of deviation markers based on the square which I dragged out over this blue area. We can arrange that in a while, but one more thing I want to show you is you can also create a cross-section scan. So if I open up my cross-section scan, here we have our cross-section. I can turn on a polyline connector. And if I zoom in, you can see that the points that we've collected have been linked up into a line, and you can see which are the areas which are above tolerance based on this cat drawing in the background, which are within and which are under. We can choose to display the highest and lowest deviation areas for this cross section. So we can take one screenshot here. You can zoom in and take another screenshot here if it's of interest to you. We can do a radius analysis in this corner. Capture another screenshot. If I close this, and we just rearrange the view, rearrange my deviation markers. We can also generate a report based on all the analysis which we've done. So I include all my features measured. Add it to my report. View the real-time update. If I scroll down again, we get the same feedback of the screenshot. We get the point cloud summary, and I explain how the histogram here works. So for the 25 deviation points which I took, you can see for each point, which is represented by one of those green dots, you get the deviation value and the out of tolerance based on your tolerance setting. Get the plain summary. And for the cross section, again, we get the histogram telling you the distribution of the points. Across the cross section, you'll be able to tell which areas have under over tolerance points. We get the lowest and highest deviation readout and the screenshots which I took earlier on. So again, you can export those in the same formats which I mentioned earlier. And that brings me to the end of today's web demonstration on the Edge ScanArm. Thank you very much. Thank you very much once again for taking the time to view our web demonstration on the Edge ScanArm today. We hope you found this session useful, and we look forward to hearing your feedback on our product. Have a nice day.